An Atwood machine is really just two masses connected by a light string around a pulley. It's pretty good to be early in the field of sciences, of a given science, because you get your name on all these simple and easy things. So this problem says, find the acceleration of the following Atwood machine, where M1 is 150 grams and M2 is 200 grams. And in class, people would walk through and do this problem. In fact, we do it a couple times, but I'm going to do it generically. I'm going to do it in terms of just M1 and M2, because that result ends up being both useful and powerful, and it's nice to see how it works together. But you could walk through the same steps using the numbers if they make you feel better. I just want to do it once as a full-on thing. So in our recipe, step 1 was read the problem, which we just did. Given those masses, find the acceleration. Step 2 is to draw a free body diagram. So for each object. So we'll have the 150 gram mass and the 200 gram mass. And of course, on the 150 gram mass, there is a weight and there is a tension. And on the 250 gram mass, there's also a weight. And now I have to be careful because these are two different things. So I'm going to call this FG1 and FG2. On the other hand, there's only one tension because the string is light, meaning it's low mass, and so it only has one tension in it, which we can use as an interesting factoid. Step 3 says constitutive equations. Constitutive equations. For us, those constitutive equations are going to be merely that each weight is really just the mass times g. So Fg1 is m1 times g, and Fg2 is m2 times g. Step 4 says write Fnet from the diagram. We also know Fnet has something else it's equal to, but right now let's just do it from the diagram. So we have Fnet1 is, and we look at the diagram, we say, oh, well, there's an Ft and there's an Fg1, but we have to notice that Ft points up and Fg points downward. The net force is their vector sum, so it has to include their direction. On the FBD, the directions are included by just the arrows, yay. But in algebra, we have to do it a different way. We'll make one of these minus. And likewise, Fnet2 is going to be Ft minus Fg2. Again, Ft and Fg2 point in different directions, so we get different signs. Step 5 is write expressions for A, usually from the problem. So we're going to go back and look at this and say, well, if M2 is more than M1, then we know that M2 is going to descend with some acceleration, which I'm going to call A0. But we also know that if block 2 descends by, say, a centimeter, then block 1 has to ascend by a centimeter because along the string, the distance stays the same. So if we play out an extra centimeter string on block 2, we have to give it up on block 1. That means that block 1 has to move upward as fast as block 2 is moving downward, and it has to do it at all times, which means that block 1 has to have an upward acceleration that is also the same magnitude. So going over here, we can say that A1 has just some acceleration up, and A2, block 2, has an acceleration which is the same size, but notice that here I have to be careful. Fg2 is pointing downward, A0 here is pointing downward. They should have the same sign. Since this one was negative, so is this. As a word to the wise, that's where a lot of students go wrong, and if you go wrong, you're going to find out that the acceleration is g, which should be a thing that puts you back on your heels and say, that doesn't make sense, and you should go looking for sign errors. Step 6 says, write Fnet equals ma for every object. So we have Fnet1 equals m1 a1, and Fnet2 equals m2 a2. I haven't really done anything there. I'm just taking second law. Step 6 is nice because it's always the same. It doesn't get you a whole lot forward, but formally from a mathematical sense, it's going to allow us to connect things that we know are connected. All right. Now we'll need a little bit more room, so I'm going to slide over. Step 7 says substitute. So I'm going to say where I have over here f net 1 equals m1a1. I'm going to substitute everything I know, which is that ft minus m1g is m1a0, and that ft minus m2g is m2 times minus a0. And again, this minus sign is going to be really important. Step 8 says solve algebraically. Find this for the thing we want. Remember, the thing we want is going to be a0. So I'm going to rewrite these equations a little bit more cleanly. That ft minus m1g equals m1a0, but also that ft minus m2g is minus m2a0, where I've just moved this minus sign to the front. We can solve this any way you want. You can just brute force solve it, solve one of them for ft, plug into the other equation. In the end, we want to eliminate ft. It's not a variable we're interested in, and it's mucking up our system. The way I'm going to choose to do that is to multiply the entire second equation by minus 1. So I'll get a minus here, and then a plus here, and then a plus here. And then I'm going to add this whole equation to the top equation. So I have ft minus ft. Hey, they go away. And then I have m2g minus m1g. m2g minus m1g, and that's going to equal m2a0 plus m1a0. To solve this for a0, I should factor. m2 minus m1 times g is m2 plus m1 times a0, and then divide over. So divide everybody by m2 plus m1. And what I'm left with at the end is that, let's do this in some nice bold color, that a0 is g times some fraction, and the fraction is the difference of the masses over the sum of the masses. To repeat, a0 is g times m2 minus m1 over m2 plus m1, which makes this particular problem we had particularly easy. It's g times 200 grams minus 150 grams over 200 grams plus 150 grams. And you notice that the grams are going to cancel out, so we didn't even have to convert them to kilograms, which is accidentally, I suppose, a nice thing that comes out. We get 1/7 g, which turns out to be 1.4 meters per second square. But the thing that I really want to focus on, the thing I want to draw attention to, is this model for what the acceleration of an Atwood machine should be. Also notice that you can think of this model as the total force on the system over the total mass of the system, as you'd expect, right? The total force, because we have m2g pulling down, but we have m1g essentially pulling that one back up, pulling in the other direction, although the direction has been bent around by the pulley. But the only external forces here are the gravitational forces. They have opposite effects, so we treat them as opposite directions. So we have something like m2g minus m1g, the total or net force on that system from the outside. And we divide the total mass because we want to use a new second law thing. So this is a quasi second law result. It sort of looks like the second law and is therefore convenient and relatively easy to remember.